Hey, this is Horner, and this is my version of drifting continents. So, back in 1910, Alfred Wegener came up with a theory called, or a hypothesis called, the continental drift. And this hypothesis really just said that all the continents were once joined together in a single landmass. And that landmass, this great big landmass, this supercontinent that you see in both of these pictures, was called Pangaea. And over millions and millions of years, these would separate due to this continental drift into what we see today. So let's take a look at what that looks like. So about 225 million years ago, we had one big landmass that they called Pangaea. And then in the Triassic area, you'll notice that it became, about two big land masses here. In the Jurassic, they kept spreading apart. In the Cretaceous, and then finally our present day, kind of what we have. So that is the hypothesis that he had, that all these continents were one continent and then they drifted apart after some time. So how do we know that that happened? Well, there's a lot of different evidence that shows this. The first one are just some land features we can see. We can look at fossils. We can look at mid-ocean ridges, seafloor spreading, and then finally ocean trenches. Let's look at the first one. The first one is just evidence from land features, and the current continents look like a puzzle piece that's kind of been taken apart. And we can tell that a lot of these pieces probably should go together. So on your notes, what you're going to do is we need to match up number one with one of the letters. And if you look, you'll see this little piece here. It looks like it fits right inside of B. So we're just going to draw a line from number one down to B. And then for number two looks like it does kind of match up with letter A. If we look at number three, we'll see that number three really kind of fits into letter D here. And then finally, number four, this little piece fits right into the eastern part of Africa. And so we could put all of the puzzle back together. We also have some evidence from fossils. So remember, a fossil is just any trace of an ancient organism, and that organism's been preserved in a rock. So Wegener noticed that similar fossilized plants and animals seem to be found very far apart on different continents, but there's no way that they could have gone from one to the other. For example, they might see that some of those fossilized plants are here, and the exact same fossilized plants are here, but they're not sure how that happened. So the theory of of this continental drift would show that at one time they were together and all of the plants were growing on these two parts, and then as they separated, they kept growing, but the plants didn't just move from one place to the other. Same thing with a lot of different animals. For example, if we looked at the Glossopteris, this is a fossilized fern, so that's the plant. But if we look at Lysostris and Mesostris, these are both fossilized freshwater reptiles, and they occur on two totally different continents. And there's no way, since they're freshwater, that they would have been able to swim across the ocean. So that's another form of evidence that we have this moving of continents. And a good way to kind of look at how this happens is to fill in this diagram. So we'll kind of do this together. And the first thing we can do is try to figure out what continents did these pieces of land in Pangaea become. And so we can tell from this first one that it probably broke off here. Kind of looks like Florida a little bit. This looks like it might be California. This must be the upper northeast. And so this one's going to be North America. So this part of Pangaea became North America. If that's true, then we've got another piece here, and it must be South America. We can see Eurasia up here, so that'd be Europe and Asia. That's what this became. And then this little piece here must be Africa, and you can kind of see it has that same type of shape. And then finally, we've got the piece down on the bottom, and that became Australia. So we've got a little piece that became Australia and even broke off here, and this became Antarctica. On top of that, remember we said that we see fossilized plants and we see animals. So we've got coral beds that occur here. And so you can see those coral beds. And they also occur here in some other places. We've got some folded mountains. We also, in this picture, have the Listoris fossils. Okay, so remember those are some of those animals. And then we have glacial deposits. So all of those things kind of came out, and we see how they are in different places. So glacial deposits down here on this picture, you'll see them here, but we also see them here in Australia and some over here in Africa. We see folded mountains both here and here, so that's where we can kind of see how that broke off. But we see these Glossopteris fossils of these plants here, but we also see them over here. So it's kind of like the puzzle has all kinds of different pictures on it, and those pictures tend to be in the just in the us seeing the folded mountains and these glacial deposits and all these fossils. So a lot of evidence points to continental drift happening. And there's our Glossopteris fossils that we see down here. Another one is evidence from mid-ocean ridges. So mid-ocean ridges rise in the seafloor like stitches on the seams of a baseball. And there's one in the Pacific that we call the Ring of Fire, and it's because there's lots of volcanic activity there. In the mid-1900s, the scientists mapped these mid-ocean ridges, and they used sonar, kind of like a bat kind of sees in the dark. That's what we did, but we sent sound waves down in the ocean, and they bounced off the floor and came back up, and we were able to see these images. Now, the vertical scale here is really exaggerated, so it wouldn't be as big here as what it looks, but there are lots of very long mountain chains under the ocean. Evidence from seafloor spreading. So you see the seafloor spreading here, how we have magma come up, and then we've got some other processes that make the seafloor kind of come apart. At the same time, we also see some older strips of rock move outward from either side. So this is some evidence that we have of seafloor spreading. It includes evidence from ocean material. So we get these little rocks here, and it's called pillow lava because when it comes up, it hits the water, and instead of making the lava that we see that kind of flows like a river, it makes like pillows. We have evidence from magnetic stripes, and in this we can see some magnetic stripes. Here's the purple magnetic stripe. So one of the things that we're going to do is we're going to show those magnetic stripes on the other side too. So you'll need to have some sort of marker or colored pencil, and we can also color in the magnetic stripes over on this side. And we kind of can see how every once in a while we'll take a break from putting some of this material in, and some of the material will have this magnetic striping in it. We also drill down into some of the areas into the crust, and when we do that we can see what a lot of this looks like. So we just take a drill, we pull down, and then we pull out some of the earth, and we can kind of read what's happened in that. So we use some drilling samples to see the sea floor spreading. Another form of evidence is from ocean trenches. The oceanic crust created a lot of these mid-ocean ridges, and that crust is destroyed at what we call a deep ocean trench. So during this process called subduction, so notice this sub means to go under, kind of like a submarine goes under the water. This plate is going underneath of the other plate. So the oceanic crust sinks down beneath this trench. So there's a trench here, and when it sinks down in, we call that subduction. So let's go ahead and fill in some of these blanks on your notes. The first one is, this is called a deep ocean trench, and this is where this subduction occurs, where we have this oceanic plate and this continental crust the oceanic plate's kind of pushing underneath the continental. Here we've got a mid-ocean ridge right in the middle where we know we've got these two plates are pulling apart. We also have the mantle down here. In location A, the crust is definitely newly formed. The crust is definitely hot, okay, right here, and the crust here is also what we call less dense. In location B, we see that the crust is a little bit older, so not inside the trench, but it's getting pushed out away from the trench. The crust is definitely colder, and the crust is more dense. And because of that, it continues to kind of fall. Gravity pushes it as we go through. So that's evidence for ocean trenches. The theory of plate tectonics. This is just a theory that describes the large-scale movements of the Earth's lithosphere. So we talked about the lithosphere, the asthenosphere, the mesosphere, and then the outer and the inner core. The lithosphere is broken into pieces, and it's separated by different cracks, and these pieces are what we call plates. So these are all the plates that we'll see. So you'll see the North American plate, the South American plate, African plate, Arabian plate, Eurasian plate, Indo-Australian plate, the Antarctic plate. There's just all kinds of plates here. And at these plates, in between each one of these plates, we have some different boundaries. There are convergent boundaries, kind of like you see in the picture here. There are divergent boundaries, and then there's something called a transform boundary. And anytime you look at a map that shows the differences between the plates, you can see where some of these boundaries are and how they differ. They also tell you which way the plates are moving. So arrows pointing away from each other are going to be divergent, and then arrows that point toward each other, like you see here, are what we call convergent. So let's go ahead and take a look at each one of these different boundaries. Convergent boundaries are boundaries that come together. So they form where two plates collide or come together, and there are different ones. There are continent to continent collisions. So like this one, this is where two plates of continental lithosphere collide, they buckle, they thicken, and this causes what we see as mountains to form. Continent-ocean collisions. This is when a plate of the oceanic lithosphere collides with the continental lithosphere, and the oceanic lithosphere subducts. It means it goes under. So sub, remember, means goes under. So here we've got the oceanic lithosphere going underneath of the continental lithosphere. Then the last one is called ocean-ocean collisions, and this is when two plates of oceanic lithosphere collide, and the older, denser plate will go under the newer plate. So this would be the older plate on this side, and this would be the newer plate on this side. The second type of boundary is called a divergent boundary, and this is when two plates are moving away from each other. This is where the pieces of the Earth's crust diverge on land, and a deep valley that we call a rift valley, and this is a rift valley here, will form. So remember, at divergent boundaries, the plates do separate, kind of like this animation shows you up here on the top. Transform boundaries are boundaries where the two plates will actually move past each other horizontally. So that means that they slide. It's kind of like if you had two books, you pushed them together, and then you slid them apart, like the two plates that you see here. A good example of this is the San Andreas Fault in California, so you can kind of see a picture of that, and here's how that boundary works. And remember, at these boundaries, the plates will actually do slide across each other, so past each other horizontally. So this one's moving in this direction, this moving in this direction. We are also going to look at why these tectonic plates move, and there are three reasons, three ways that they do this. One is called mantle convection, one is called ridge push, and the other one is called slab pull. So in convection, we have hot and less dense rock will actually rise. So you'll see how the less dense, hotter rock here comes up, and then it cools, and when it gets to the top, then it falls back down. So you can kind of see the arrows. Same thing here. We've got these hot, less dense rock will start to rise. It cools, becomes more dense, and then it comes back down. And when it does this, this drags the overlying tectonic plates along with it. So you'll see how this one's curling in a clockwise fashion, and this one's going counterclockwise. And it does that. It moves the rock above it, starts to move that lithosphere above it. In ridge push, we have this convection going on, and as the ridge up on the top, so these mid-oceanic ridges, so they happen near this mid-oceanic ridge, as it cools, it gets heavier, and when it gets heavier, it gets kind of pushed down the hill. So we have, it might be maybe a volcano's forming here, or just we get a little bit of a ridge, and as that rock hardens and gets heavier, it will move down, and so we call that ridge push because it's getting quote-unquote pushed away from the ridge. The last kind is called slab pull, and this is the force that the sinking edge, so here's the sinking edge of the plate exerts on the rest of the plate. We also can see that sinking edge here too. Kind of like if you had, maybe if you put a towel on top of a table and then you pulled down on one end of the towel under the table, kind of pulled it off the table. So the rock at the trench tends to pull the other rock down, so it's pretty heavy and pretty cool here, and this always tends to happen at the edge of a subducting plate. So we see how this is sub, remember sub means to go under, and it's pulling it under, so we call that slab pull. And that is the end of this PowerPoint.